Hi, everybody. So I was looking at the notes from times where I've previously taught this class versus where we are now. And as it turns out, we are doing quite well in terms of covering material. So today's materials will maybe be a little shorter on time and a little more focused on some problem solving so that you have a chance to take the concepts that we've learned to date and apply them to some potentially real world type situations. So last class, I left you with this problem that was based off of a previous problem, focusing on our friend Dave. If you remember the previous problem, Dave had used excessive amounts of water and had dropped his total head by quite a bit. And we used the groundwater aquifer compaction equation to try to get an estimate of how much compaction the aquifer was going to experience. So this particular problem I left you with plays off of several previous problems, and at first blush it looks pretty simple, but there's actually a number of steps where you have to go back, use previous equations or previous data. So let's look at this question again. So Dave has a new neighbor who put in a new well into the same confined aquifer that Dave had compacted at his place, if you remember the previous question. Dave's neighbor heard about Dave's problem with ground settling due to groundwater extraction and wants to avoid, obviously, the same excessive aquifer compaction that Dave dealt with. So Dave's neighbor would like to keep compaction to a very small amount, just 5 centimeters. How much total head loss can Dave's neighbor allow to keep this sort of minimum level of compaction? So what we're going to use, again, is our aquifer compaction equation, which is here. I'm just going to write it down and then we can discuss it. So there's the equation there. And some of the values that came from the previous question were, we have our alpha value from Dave's equation. It's 1.8 times 10 to the minus 8th meters squared per Newton. Remember, B equals the aquifer thickness. And from the previous example, it was 45 meters. Change in thickness. Remember, Dave's neighbor wants to keep the change in thickness to 5 centimeters or 0.05 meters. And then dP is the change in pressure in your aquifer. And going back to yet a previous equation, change in pressure is calculated by the density of water times gravity here on Earth times H, which is the change in head. And this is ultimately what we want to figure out. We want to find out H, again, is the drop in head associated with that pressure loss. So if we go back to our equation, what we're ultimately going to want to solve for is change in pressure, because then once we have the change in pressure, we can calculate how much head drop is needed to create that change in pressure and still stay below this 5 centimeter threshold. So if we rearrange our equation here to solve for the drop in pressure, we then end up with dB over B over alpha. Now we're going to switch over here to the next slide. We can then put in some values. We know we want to keep this drop. Oh, that should be meters because I already converted it. We want to keep the compaction to less than 5 centimeters. The original aquifer was 45 meters thick. Alpha value 1.8 times 10 to the minus 8 meters squared per Newton. And remember that this is dP also equals rho GH. H is the quantity we're interested in. So that equals dP over rho G. And if you calculate all of this out, first solve for dP, plug dP into the equation, here and here. Density of fresh water is 1,000 kilograms per meter cube. Acceleration due to gravity, 9.8 meters per second squared. If you plug all this in, you should end up with a value of H equals 6.25 meters. And what this means, if you think back to how this equation works, is this is the amount of head loss that corresponds to an aquifer compaction, which is our delta B, change in thickness of the aquifer, of 5 centimeters, or 0.05 meters. So, in reality, what would happen is Dave's neighbor would drill a well. He would measure the total head value, just what's the elevation of the water column in his well. And then as he uses water, he has to do so in a manner where when he pumps, he never lowers the total head value by more than 6.25 meters, or roughly about 20 feet. So how hard or easy that is depends on a number of factors, but Dave's neighbor would simply have to monitor this head loss and keep it to a minimum. Okay? So go through this equation. If you have any issues or if there's something you don't understand, if we go back up to the top of this slide, if you look at the units for this equation right here, meters canceled. So you have no units on top. It's just dimensionless. And then on the bottom, we have meters squared per Newton. So dP equals 1 over meters squared per Newton. dP therefore equals Newton per meter squared, which is also a Pascal. Pressure should be measured in pascals, so that all works out. So if you have any questions on how the units are working, how the equation works, shoot me an email. I'll set up a time to meet with you, or we can go through it at the beginning of class next time. So if you're having difficulty, make sure you let me know, because I know, especially for the students who are online all the time, I don't get to interact with you guys face to face, and it's a challenge for me as a professor to know if you're really understanding the material. So please, if you're struggling at all with this stuff, send me an email, because if I know that one person is struggling, it's probably a pretty good bet that most of you are struggling. And I can spend some more time, since we're doing fine on progress in terms of the concepts we're covering and how much time we have this semester. I can certainly spend more time on some of these examples, give you more examples that hopefully help you see the relationships between the concepts we're learning, the equations that we use to calculate various entities, and what these calculated values that you come up with actually mean. So again, let me know where you are on this. Don't just sit back and hope for the best. I want you to be able to really learn this material and do the best you can with it. So what I'd like to do is give you another little equation that uses several of the things that we've learned so far, and give you a chance to see if you can apply it. So here's a new question for you. So let's say we have a confined aquifer. Again, have a image in your head as to what a confined aquifer looks like. And this confined aquifer is 33 meters thick. And it's 7 kilometers wide. So for you true Americans who don't know your metric system yet, 33 meters, about 100 feet, 7 kilometers, somewhere a little less than 5 miles. Okay, so this is a good size aquifer. And there are 2 wells. That go into this aquifer. And they are about 1.2 kilometers apart. So we have a confined aquifer, 33 meters thick, 7 kilometers wide, and we have 2 wells that are going down and penetrating this aquifer, and they're 1.2 kilometers apart, 3/4 of a mile. Okay? Let's give you some data. The total head value at the first well is 97.5 meters. Total head value at well 2, which is 1.2 kilometers away, (89 meters). The hydraulic conductivity is estimated, and they would probably get this value from drillers or from hydrologists in the area, but you can get estimates for hydraulic conductivity for various types of aquifers, sandstone, shales, whatever. You can find these on tables in the internet and various tables in groundwater hydrology books, or you can get them from well drillers. Sometimes know them, and definitely hydrologists that work in the area get them. So these are data that are probably available for most people if they want to do a little digging. So the hydraulic conductivity is estimated at 1.2 meters per day. Remember, this isn't actually a velocity of groundwater movement, even though it has a unit of velocity. It's simply a property that the aquifer has. The higher this number, the easier it is for water to move through it. The lower this hydraulic conductivity value, the harder water is to move through it. But in order to have water move in, you have to have a pressure differential, which we have here because we have different total head values at 1 versus 2. You see the total head value at well 1 is higher than total head value of well 2, and water will always move from regions of high pressure to low pressure. So we have a pressure differential. It's higher at well 1, so that means that water is going to move from well 1 towards well 2 just because of the pressure differential. And it's moving through rock that has a hydraulic conductivity value of 1.2 meters per day. That could probably equate to something like a sandstone. If it was a shale, that value would be lower. It's harder for water to move through most shales than sandstone. If it was a cavernous limestone, where water could move maybe even easier than through a sandstone, then this 1.2 meters per day value might be higher for that particular rock type. Okay, so that's the data we have so far. I'm going to give you a little bit more information. We also know the effective porosity. Remember, we have porosity and we have effective porosity. So regular porosity is just how much of the rock is taken up by pore space. Effective porosity is the pore space where water can actually travel through. Because some pores don't connect to other pores. So some of your pores might be there, but they're not an effective pore in terms of how water can move through. So for this case, the effective porosity is estimated at, let's say, 5%. So the question I have for you is, what is the daily flow? How much water flows through the aquifer per day? What is the daily flow and this will probably be in meters cubed per day of water through the aquifer? And I've given you a lot of equations so far this semester, and one of the challenges for you is to try to figure out which equation do I use to solve each problem. Well, I'll give you a second to look back through your notes, and I'll just wait here a second or two to see if you can figure out which equation that we've used in the past 2 or 3 classes would be most appropriate for figuring out how much water would flow through this aquifer every day. So I'll give you a minute or two to look back through your notes. Okay, so if you spent some time looking at this question and looking at the equations that are available to you, perhaps you figured out that the equation for Darcy's law is probably the one that fits the problem the best. The one thing that you always have to look at as a scientist is take a look at the data you're given and see which mathematical model fits it the best. And sometimes not every mathematical model will perfectly fit every bit of data that you're given. And sometimes you're given more data than your mathematical model needs. And that's what I did to you in this case. As it turns out, to solve this problem, you really don't need any information on the effective porosity. Because what Darcy's law does is it gives you a Q, which is a flow rate, a daily flow rate, which equals negative K, the hydraulic conductivity. A is the cross-sectional area, and the cross-sectional area of your aquifer, remember your aquifer is 33 meters thick and 7 kilometers wide. That's a cross-sectional area. I'll draw you a little diagram here on the next slide to sort of illustrate that. And then you have your hydraulic gradient, change in head or change in distance. So if you look at the problem here, you actually have all of these variables covered. And then you also had some extra, which we will avoid for this part of the problem. So let's go over and sort of draw this out. I like to draw things to hopefully show you, a mind's eye picture of what these equations are trying to estimate for you. So let's go and draw this out. So let me see. I'm going to use red as the aquifer. Wish I had a brown, but I don't have a brown. So we have an aquifer. This is not going to be to scale because remember, this is an aquifer that is 7 kilometers thick, or 7 kilometers wide, and 33 meters thick. And maybe it's something like a sandstone. Okay. There's a number of different ways you could draw this out. I'm going to draw it looking like this. And what you have is you have a certain amount of water flow that's moving through this cross-sectional area that's 7 kilometers wide and 33 meters thick. So how much water is going to pass through there every day? That is the question that you need to determine. Okay, so again, up above this, let's see if I can draw this. We have our ground surface. And remember, we have one well, let's say right here. And then we have another well that's going to be 1.2 kilometers away. And it's going to penetrate into the aquifer back here. So up here, your water rises to, let's just say, 89 meters. I could make this well one and make it 98.5 meters. And then back here, or 97.5, the water is a little higher, 97.5 meters. Okay, and it's getting a little messy. Let's see if I can fill this in. So this well here rises up, so that has a total head value of 89 meters. And back here, the water rises up and has a total head value of 97.5 meters. Over a distance of 1.2 kilometers. Okay? So, if we simply take Darcy's law, Q equals negative K A DHDL. Remember our K is 1.2 meters per day. Area I'm going to convert this to meters. So 7 kilometers is 7,000 meters times 33 meters thick. dH over dl. The difference in height between the two wells, 89 minus 97.5 meters, over change in distance, which is 1.2 kilometers. I'm just going to convert that right away to meters. There are your various values. So Q equals negative 1.2 meters per day times 7,000 meters times 33 meters. Need to make a little room here, so I'm going to erase this, finish out the problem, and then times your hydraulic gradient, which was 89 meters minus 97.5 meters over 1,200 meters. If you multiply that out, these units here are going to cancel. You're going to end up with, that value becomes negative 8.5 meters over 1,200 meters. So the meters cancel out. Meters times meters times meters is going to give you a meters cubed over day. So meters over day, meters cubed per day. That's a flow rate. And if you do the math part of it, you should end up with 1,964 meters cubed per day. So that is how much flow, that's how many cubic meters of water is going to pass through this surface area right here, given an 8.5 meter drop in head over a 1,200 meter distance between the two wells. Okay, so you have a pressure gradient up here that's going to be driving water this direction. It's going to be driving it through this cross-sectional area right here, and then depending on the ease to which it can move through that rock, which is our K, our hydraulic conductivity value, you can then calculate total amount of water that moves through it. So take some time with this equation. Make sure you understand this. This is the basis for all groundwater movement. We're going to start looking at how wells will affect groundwater movement in our next problem. So make sure you have a basic understanding for how Darcy's law works. And this problem should do it. So if you're having trouble again with these concepts, going through these problems, and you think you would benefit by having more, let me know. If I don't hear from anybody, I'm just going to, the only thing I can really assume is that this is going fine for all of you. So if you are having problems, please let me know so I can give you more problems. I don't want to give you more problems. I'm not the sort of professor who just wants to throw a bunch of additional homework at you just for kicks and giggles. I only want to increase your workload if you're having trouble understanding this. So you have to communicate with me. Let me know if you're getting this. Let me know if you're having problems with this. If you need more work, I'm guessing everybody else in the class probably needs more work too. And I can spend next class just doing some equations, or we can move on and do some more work. So let me know how you're handling all of this. So we will continue on, and then next week we will have face-to-face class for the face-to-face students.